All right, welcome to the fourth and final part of the Introduction to Axiomatic Design. I'm Chris Brown, WPI Mechanical Engineering Department. So in this section we will go through some special parts of coupling, particularly inherited coupling, physical integration, measuring the design process, and then some concluding remarks. So one of the things we learned how to do the last time was decouple coupled systems, in order to eliminate imaginary complexity and avoid non-productive iterations. So one of the things we want to do is build a design matrix and show interactions and then find the best order of adjustment. Now there's an interesting exercise that you can download. It's in an Excel file, and let me bring that up for you. And this is an exercise that was created by Dr. Larry O, formerly of General Motors. And he publishes and presents papers on axiomatic design. And this is a neat little exercise. It's kind of a game. You have the target values for the FRs that you want. You have the actual value for the FR. And then you have the value for the DP. So your job is to try to adjust the DP so that it coincides with the FR. And you can do it by sliding this thing up or doing the arrow there. And now I've adjusted DP1, so FR1 is in tolerance. And then I can decide if I want a larger tolerance band. And there we go with the same thing for this one. And my target value is 0, so I bring this down to 0, and I go, whoops, it goes the other way. All right, so there's 0. So I've adjusted that one completely. Now, demo 4 is a little bit more interesting. And so as I adjust DP1 to try to get FR4 in tolerance, I'm looking at what's happening to the value there. I'm just about there. Whoops. Okay, so I could call that close enough. And now I start adjusting the next one, and we see that, FR1 is now out of tolerance because there is some coupling. So you can try to figure out what's the right order of adjustment in order to adjust the DPs to satisfy all the FRs. Now, and it's most fun to do this without looking at sort of kind of where the answers are. And there's your matrix coupled design. And you can actually go in and change these and set up some things. And so so there's some intermediate levels at 2 and 3, and you can make more. And so have fun with this. This is what passes for fun in this course. All right, so let's go back to, I think you'll have a great time with it. All right. So remember, at each level, the children should be semi-min decompositions of the parent. So that means collectively exhaustive, so that the parent is completely described, and mutually exclusive, so as not to introduce coupling at the FR level already. And we'll take a look at some more details on that. All right, so here is an important theorem. If the children are coupled, then so are the parents, provided that the decomposition is really semi-min and that the tolerances are also inherited. Let's see what that means. Well, the first thing we need to do is look at the design matrix and see where the patterns are. And what we're talking about here, if a child in one part is coupled with a child in another part, and I'm sorry, that's not anther part, but should be another part, then the parents should also be coupled, unless the influence is very small, or the decomposition is not complete, in which case you better go back and fix the decomposition. So let's see what that means. All right, so here's a little problem. Let's provide intercity transportation, and so then we have sort of some sort of intercity transportation system. So this is cut and paste out of a Claro. You probably recognize it by now. FR1 could be transport merchandise, FR2 transport personnel. So as you set this up, you might optimistically say, well, let's suppose it's completely decoupled. And then you see how we're doing it. So in the United States, we've decided that one set of roadways would be sufficient for this. And so if we take a look at the DPs, and this got truncated here, this should be trucks and this should be cars. But the coupling comes in that we've got the interstate highway system that both the trucks that are transporting the merchandise and the cars have to ride on. So this is the kind of thing that you think about when you're driving someplace and the trucks are doing the 3-mile pass where one's doing 64.5 miles an hour and the other's doing 65 miles an hour. That's going up the hills, and then they switch going down the hills. And so you never get by them until it breaks into 3 lanes, or by luck the flat or the hill lasts long enough so there's a gap opens up between them. All right, so what happens? There is coupling now. We notice when we get to this level in the decomposition, since we didn't have anything besides the interstate highway system to satisfy the roadways. So primary, here's where we see it primarily. Whoops, here is the child of FR2 is coupled with DP 1.2. So DP 1.2 interstate highway system is influencing the child of FR2. So our personal transportation is disrupted by the merchandise. So this doesn't mean I'm against interstate highways or the truckers or anything. It just means I'm in favor of railroads. All right, so then we need to promote this. So if DP 1.2 is influencing FR 2.2, then that means DP 1.2 is also influencing FR2, because if you influence the child, you influence the parent. So there is an influence here. Whoops. So there's an influence there. Now that doesn't automatically go into the matrix. You'll notice when you enter this X in Aclaro, this one doesn't change. So Aclaro does not recognize this. Then the other thing is you say, well, DP 1.2 is influencing FR2. That means DP1 is also influencing FR2, and now that should be an X. So if you started off optimistically with a diagonal matrix saying, I think we can solve this problem, and then you find out that nobody can get their act together to build good railroads in the United States, and you go, uh-oh, we're stuck with highways for transporting everything. And in some ways, if you have 3 lanes, don't allow the trucks in the 3rd lane, that's a kind of decoupling. That's an extra DP. So you could say the merchandise transportation is for the right lanes, and then we can decouple it with some extra lanes. Although if you've got heavy traffic, you notice that doesn't work either. But in any case, now as we work through this whole thing with all of the coupling complete, we can see that this is now a completely fully coupled matrix. And they turn pink because there's no way to resolve that. So you can find the little click and click on decouple this, which is provided in Aclaro, and you'll notice that it can't decouple it. So you're stuck with this coupling, and you notice that it's a bad design. Actually, as we think about this, when you notice some sort of frustration with something, see if you can find out, or see if you can find how it violates axiom 1 or axiom 2. And I think you'll find out with many systems that happens. Think about this too. Look around you. Think about all the things you've done today. These are all things that have been designed. And if you find some frustration or something that doesn't seem to be working well, in all of these design systems, you can probably find an interpretation of that design that leads to a violation of axiom 1 or axiom 2. And this is a useful interpretation because it can help you find some solutions to that design deficiency. The thing to keep in mind is that almost everything we encounter has been designed. The way we do design influences everything. One of the points, and I'll get back to this at the end of the lecture, though, that's important. Often when I talk to seniors who have been studying engineering for 4 years, and I say, all right, you're doing your senior thesis, your MQP. What are you doing here that you could not have done 4 years ago? What is different about your design method? I understand you've learned a lot of analysis, but what is different about your design method that, that raises it above the level that you could have done before you came to engineering school? And many times the seniors can't find something that they're doing different in their design method. We have not done a good job of teaching them design methods, which is one of the reasons we're doing this in a grad class. All right. I want to go through an example. This is something we designed for NASA back when NASA actually put people into space and brought them back again. So this is a runway. This is to better design runways, and the objective here was to see if we could decouple friction and wear on the same runway surface. Now, to do that, we had to we wanted to see if we could have high friction and low wear, and so we decided we needed to measure the pavement and understand it better. So here was FR0. Let's link the pavement texture, is what the civil engineers like to call the roughness of the pavement, to performance. And so then we needed some system for linking pavement texture to performance. All right, so FR1 was measure the runway texture in sufficient detail, and then FR2 is analyze the measurements appropriately. Had some constraints, so a constraint on time, constraint on money, and constraint from human resources. So this is what we could get in a grant from NASA. All right, so DP1, we wanted an adjustable texture measurement device. Why does it have to be adjustable? Because we're not sure what we need to measure yet. There is not sufficient information or knowledge about pavement textures and wear, or pavement texture measurement and wear and friction. So we want to be able to choose our sampling size and resolution to the greatest extent possible. DP2 is a computational system. All right, so the next step is let's take a look and see if they are coupled. All right, so we had selected these so that they to have an intended diagonal matrix. All right, will the measurement device influence the analysis? So what do we have here in the A21 position? And if the measurement isn't good, or if it isn't sufficient in resolution to make the measurement at the scales that are causing the wear or responsible for the friction, then I will never be able to make those correlations. Therefore, there should be an influence there. So that should be an X. Now, I need to work very hard then in a design problem like this to make sure that the A12 is a 0. Otherwise, I need to redefine things in order to avoid a fully coupled system. So what is DP2 doing, the computational system, to the measurement system? Well, the computational system doesn't drive the measurement system. The measurement system comes first, and I can make that independent. So this is going to be an O. So this is an X, that's an O. So I have a triangular matrix, as shown here. So the measurement system, it notes, and we'll talk about sequential coupling in a moment. So both sequentially and physically, the measurement will influence the analysis. So it's quasi-coupled or decoupled. All right, so we advance now. We've got level 1 done. So we have done this level in the matrix. We have checked this, and now we can go down and let's take a look at DP1. And this exercise is going to be looking at the details on DP1. I'll show you some outcomes from DP2. So the FR1Js are defined in the context of DP1, which is this scanning laser measurement system. All right, as I said, we don't know what resolution or size we want, and time to measure is also an issue. and that's because we're taking measurements on runways, and we need to get out of the way so they can use the runways. Runways are a big investment, and we can't tie it up with the measurement. So they need to be adjustable, therefore they are FRs, and we need to control them. So we need to figure out how we're going to control resolution, size, and time so that it is not overly complex and we can adjust them without iterating. Are these things coupled? Well, the first guess is, yeah, I can't choose any measurement size and then choose any time. Similarly, I can't choose any resolution and choose any time, because these things are obviously going to take time. So it looks like it should be coupled. So the actual device, so we're concerned here about how to control this device, and that's what we're designing as this control system. This is what the actual device looks like. All right, so this gantry that is here that sort of holds things up. So there's one of the legs of the gantry. And then we've got some scanning tables that go this way and that way. So we can scan the sensor, and this is the height sensor that goes there. We can scan that over the surface. And we actually have one more table here that can move the height sensor up and down, because the standoff distance is got to be maintained within a certain range to actually measure the surface. And there's a picture of a surface. I'll show you a picture later of this on an actual runway. So here's what the measurement pattern looks like. And one of the interesting things, actually, if we think about this in the context of manufacturing, one, it is a kind of quality control system, and while it's being used on runways, it could be used on different kinds of manufactured products as well. The other thing is, what we're talking about is taking measuring a height and then moving along and taking another height. That could also be processing the material, for example, some sort of laser thing, some ablation, so as we do any kind of scanning operation on a surface, to clean it, to cut it, to modify the surface, this could be a manufacturing operation or parallel to a manufacturing operation as well. Let me point out a couple things. So then, as we move over a certain distance in x, there's our resolution in x, and that would be in what we call the tracing direction. So we move across and look at all these measurements, and then we index over, and then we move across and look at and take all those measurements. So then the sampling resolution in y is here, so there is the y resolution in between the two traces. So we're tracing in x, scanning in y, so you have an idea what this looks like. So the resolution, we're going to say, is controlled by this what we call the sampling interval, because each one of these little blue things represents a height sample that we've made with, as you'll see in a moment, or as you saw in the previous slide, the laser height sensor. All right, so what do we need? We need to provide for an adjustment of the resolution and the size and the time. So what are the decompositions then of, for example, resolution and size? Now, I hope you've given this enough thought so you may have some ideas about how to decompose these. And here's a question: do we need another level in the hierarchy? So how do you figure out if you need another level in the hierarchy? Well, the rule is that you decompose until the solution is obvious. All right, so if I look at this and go, I can see how to do it. All right, great. Supposedly, Feynman was able to look at very tough problems and write down the answer. So if you're to the Feynman point where you can look at it and write it down, then you can stop doing the decomposition. Sometimes I find, though, taking the decomposition one more step than I think it needs to go reveals that I didn't know as much about the system as I thought I did. Anyway, when we have to decompose something, all right, so here, let's see, where did we go? All right, So what I'm going to do for you is I'm going to upload an Aclaro file that you can use, and at this point you can put it in and start doing the some of the things yourself. So so here is the result of some Aclaro work, and we'll go over this in more detail later, but for now you can load the file and give it a try. All right, so so the next thing we do is list the DPs that satisfy the FRs. So control resolution, we need control systems. So you can see that this is control and control system, and all we're doing is really restating the FR in the DP. So this doesn't give us a whole lot of new information, but what it says is new knowledge about how we're going to solve this problem. But what it does say is that we've got three separate systems that are going to control these three things that we're trying to control, and we know that's a good approach. So, so at this point, what do we know? Well, these seem to be well, our first thing, we've selected each one to influence those things. So we have, as you can see, a diagonal matrix. And at this point, this really expresses perhaps our optimism about what we can do to keep these off-diagonal terms to 0. Although looking at these things, we suspect we won't be able to do that. So now let's decompose and see what's happening in the level of the child interaction, where we may have to get more specific about these systems. So now here's the thing, as we control the resolution, all right, so how are we going to decompose control resolution? That's the question we asked a few moments ago. All right, so we can use a Cartesian type decomposition, and that would seem to make sense as we looked at our device. It's a Cartesian device, so it's measuring sort of x, y, and z. That's the pattern. So let's do a decomposition that makes sense in a Cartesian coordinate system. All right, time. How do we decompose time? Well, we've got the tracing time, we've got the dwell time, and we've got the number of traces. Then we've got the control the measurement region, and so now we've got the tracing length and the scanning length. So in these cases, then we need to look and say, well, is this collectively exhaustive and mutually exclusive? We could ask the same question here, and it looks like we might be missing. Let's know, we could control the tracing time, control the dwell time, and control the number of traces. No, I think that's complete. I don't think we're missing anything there. But you're certainly entitled to look at this, and you should be looking at it critically. There may be some other solutions that we haven't seen. All right. So now let's see what we found, and we've put the variables that we're going to be using, as you can see, in the decomposition in Aclaro, so we can keep track of what we're calling different things. All right. So now let's take a look at the data acquisition, or the DPs. So so now we're starting to get more specific. We need some data acquisition rate setting, so the D to A, the distance between the trace settings. This little arrow means there's more to follow that you didn't get to see because I didn't expand it far enough before I did the screen capture. And then the height sensor system. All right. So so what's controlling Z? This height sensor. What's controlling Y? The distance between the traces, as we saw before, and then the data acquisition rate setting. All right, so then what's controlling the tracing time? Well, the tracing speed. Dwell time, this is really sort of the acceleration control. And then the number of traces, so that's a setting that we're going to make for the number of traces. And so let's see, and then finally we've got the tracing length adjustment and the scanning length adjustment. All right. So save whatever you've been working on, and then you can take this SLP as the scanning laser profiler file, which I will put on my WPI for you, and then you can download that and give that a try. Let's take a look at the equations now. Now, it's great when you can say, all right, here's an equation that I can write for the FR, and I can actually put functional tolerances on it. So the FR was provide some resolution, so we'll call this the resolution branch. And overall resolution could be in 3 dimensions, and we could do some sort of vectorial kind of addition. And here is in Cartesian space, and here are the 3 resolutions. Well, how did we figure this out? Now, we do the same thing for the time, and then the same thing for the size of the measurement region. Now, how do we come up with these equations? This is really by inspection, right? So we've got so many traces that we're going to do, and then how long is it going to take to do each trace? It's the sum of those things. So we do a little multiplication there. So I'm suggesting that in this case, you can write these equations down essentially by inspection. So here are the FRs, there are the DPs. So here is FR, and I should have put the numbers on here, would have made it easier, but all right. So here's the resolution in the X direction. This turns out to be influenced by the data acquisition rate, and then resolution Y is in the distance between the traces, and resolution in Z is the height sensor. All right, so where else are things showing up? Well, let's take a look at the tracing speed. So what we have here is a list of DPs, and we're trying to see how they're divvied up. So the tracing speed is also influencing the resolution in X. So clearly we see there's 2 things here. So 2 of our DPs are influencing this FR, so clearly we've got some coupling. The tracing speed also shows up here as we decompose these things. Now, in some cases, you can see I haven't written a full equation. I'm just saying this, the dwell time is a function of the acceleration down here and the tracing speed. So I've got to speed up to this thing, and how long is it going to take me to get there? Well, it depends on what kind of acceleration I can get out of my tables. And so anyway, so as we go through here, we can say, oh, the acceleration shows up there. Let's see, the number of traces shows up in 2 places. So clearly we do not have a fully independent system, and we've got some coupling going on. So there's the length of the trace, there is the scanning length. All right, so we have some coupling. Now, one of the hints is you're developing equations, and as I said, these are, those are just based on simple kinematics, and just simple things where, okay, I can figure out what the resolution is for this spacing and what my data acquisition rate is. So it's basic. Those were sort of kinematic equations. Keep track of the units and the FRs. So the units need to work out. FRs, DPs, and PVs in the design and process matrix. So that's a check. If the units don't work out, the equation doesn't work out. It's a necessary but not sufficient condition. So what do we have here if we start looking at the influences that we've seen? So we thought we were going to have some off-diagonal terms, and we do. So let's check for inheritance. So those are the things that we noticed at the child level. So here is this little section represents how the children of 2 are influencing the children of 1. So children of 2 influencing 1. So clearly we need to have some kind of inheritance. Here's how the children of 2 are influencing the parent of 1. So we need to have some inheritance that goes from there to there, because this is now FR or DP2 should be influencing FR1 because they're one of the children DPs is influencing one of the children FRs. So here we have, here we have some of the inheritance shown. So let's take a look at how this goes. So there is 1. So that's how we got this one. There, well, let's see. That's the first one that we looked at. Here's the second one. So we get that one and that one, our x's. All right, so here we're going from, it looks like I missed there. That should be actually up to there and not to there, so that should be going that way. All right. Now, when I take a look at the higher level interactions and collapse the matrix, which you can do just by clicking on these things in Eclairo, you can see that we have an upper triangular matrix. So that means the order of adjustment is just the opposite of 1, 2, 3. So it's 3, 2, 1. Okay, so what we can do is reorder and renumber in Eclairo, and then make this a lower triangular matrix, and now we can clearly see the orders of adjustment. So here is the device itself, actually, at the Wallops Spaceflight Facility, which was used for suborbital NASA flights early in the space program. And it's, but this is one of their runways. The day that we were here, one of the days we were there making the measurements, they've got several different kinds of pavement, and they had a workshop where people came in and test their friction testers on the different pavements and could compare them. This was the backup landing site for a carrier that was doing some training. So sometimes a pilot can't get into the carrier for some reason, and they're running low on fuel. This is where they would go. So, so this had to, there's some other FRs that meant you have to be able to throw this in the van and get off the runway quickly, because there could be a thirsty carrier plane that's coming in there to get refueled. Okay, so here's one of the measurements that was made, 3D sort of rendition of the surface. There's a picture of the surface. This was textured with what's called a skid abrader and a medium texture. So as the runway wears and gets smooth and gets full of junk, you can bring something in to bring the texture back, and that's what it looks like after you do that. We developed some analysis. I won't go into the details here. If you're interested in this, there is a course on surface metrology every other year in C-term, and that can be taken remotely or at WPI. And this is this analysis method we developed at WPI. It's in the ASME ANSI standard. We now have a new revision of this from 2009. So you can see about it there. It's also supposed to be in the new ISO standard. Anyway, this gives us some ways of appropriately analyzing the surface. And Bill Johnson, in his doctoral work, showed that with the appropriate analysis and a neural network, you can find that you can actually predict the runway friction from different parameters. 2 of these that we developed at WPI and 2 that were pre-existing. So that was the friction part of the problem. The wear part of the problem, actually the first look, the graduate student thought, I've messed up. It doesn't all fit on a line. And then he realized, actually, we're hoping that this won't be coupled. And so what this shows us is here's the wear rate, there's the friction coefficient, and so this is a system that is looks like it's uncoupled. And here is the pavement, for example, that has high friction and low wear. You'll notice that this is all in sort of the lower triangle of this system, so there's nothing up here in this space. And the reason for that is, what would be a good thing to put there? This is a manufacturing class. We haven't actually done it, but my guess is that this is where grinding wheels would go. Let's see, I need an N in there, don't let's try that again. We'll repair the R. No, we won't. We'll do that, and we will try to repair the R. I-N-D-I-N-G, grinding. So this is abrasive media. And this is pavements. All right. Just a few notes here. The order of adjustment of the DPs that we found was not intuitive for me, and so this was an important exercise to get those that order of adjustment so that we could adjust this system without iterating. The design is part of what allowed us to do this and successfully predict friction on runways. And as far as I know, there's no other research group that has been able to predict tire pavement friction based on measurements of the texture. All right. Now, the last thing that we need to do is look at integration. If you remember back to the first lecture, there were two parts to the process. One was the decomposition. So we zigzag, we get everything decomposed, so we know what all of the elements are that need to go together. And in the last lecture, we looked at the solid models where they're all put together. So we need to figure out how to assemble something so that we can maintain the independence. So the decomposition gets us to all the little elements, and now we have to figure out how do we put those together appropriately. All right, so we want to integrate these as much as we can into a single physical part. Now, there are some people that misunderstood axiomatic design early on, so this is already 1990. And we see some of the critiques of axiomatic design is it requires too many parts, and in fact it says, no, you want to minimize the number of parts, but you need to do it so that you avoid what I call integrational coupling, and that's between two DPs. Here's an example from my old Subaru station wagon of integrational coupling. And I think this resulted because the Japanese, at the time this car was designed, did not appreciate that you couldn't sell cars in the United States without cup holders. Many American cars have got more cup holders than seats. We all want to have a beverage or two available to us while we're driving. So in this case, where is the integrational coupling? So if I have an FR that says adjust, say, the defroster, those features are there. Or if I have another FR that says change the tape in the tape deck, those are there. And once I deploy this, here's the cup holder. Once I deploy it and put something in there, I have what's called integrational coupling because my access to the controls for the defroster and my access to changing the tape are limited. So when I need to do that, I have to take the beverages out, sort of hold them between my knees, and change the tape or adjust the stuff, and then put them back in. So this is one of the indications that it's a poor design. So how can we take a look at this? Well, you can set up a DP-DP matrix, very similar to the DP-FR matrix, and then you can say, all right, what is DP1? How is DP1 interacting with, of course it interacts with itself, so we're not putting anything important there. But then come down and say, well, is it interfering with the tape deck and the radio? And you go, yeah, it is, so let's put an X there. Well, is it interfering with the ventilation controls? Yeah, it's doing that too. All right, so DP2. So now you have to decide sort of what's more important, right? So is DP2 interfering with the cup holder? Well, no, it isn't. It's the cup holder that's getting in the way. Is DP2 interfering with the ventilation controls? No, it certainly isn't. They're separating it on both. DP3, no, it's not interfering with the cup holder. So we have these two X's, And any x's, any off-diagonal things in this matrix indicate that there is coupling. So this isn't like, oh, this is a manageable system. It is the cup holder is in the way here and here. What are you going to do about it? And if you go out and get a more recent Subaru, you can see what they've done. They did address that question. All right. Functional independence does not require physical separation. Axiom 1 refers to the functional independence. There's an example in one of Sue's books about a beverage can, and he claims there are 12 functions that can be identified. They're physically integrated onto the same can in one physical entity. So why don't you take a beverage can when you get a moment and see if you can find 12 different functions and the 12 different DPs, and you may actually see some things differently than Sue did. Let's see. All right, what is sequential coupling? Well, we mentioned that briefly because when we can't analyze a measurement that we haven't made, so in a sense, the analysis system is coupled to the measurement system. In manufacturing, frequently in production lines, we can't tap a hole that hasn't been drilled yet. So how do we handle this? So, and if the other problem is if the hole is drilled in the wrong place, we can't go and tap it in the right place. All right, so there is clearly some coupling, and we call that sequential coupling. Now, the advantage of decomposing coupling in different ways, because even if we get the FRDP and the decomposition into a diagonal matrix completely decoupled, then we put it together and we go, this is coupled, what happened? All right, so maybe it's coupled because we didn't recognize that there was physical coupling in integrational coupling. And so what do we do when there is sequential coupling? Because we go, geez, this seems to be coupled. So we can put some constraints in and say, all right, we need to have interface constraints so that the output from one station, say manufacturing, is not going to influence the other one. So they can be designed independently once the constraint is understood. So in the drilling and tapping example, the constraint is you got to get the hole within some tolerance that will allow it to be drilled properly. Now, and we can go on to some elaboration with that. Now, the other thing is, let's introduce another FR, and that's an inspection station. And so this requires an additional FR-DP pair. And say, all right, before it goes to the tapping station, we're going to inspect to make sure the hole got in the right place, and we're not going to send that piece along to be tapped if it's not drilled properly. And this fits in with what J.T. Black, a retired professor at Auburn who's done a lot of work in manufacturing systems, and by the way, had the same doctoral advisor, Branimir von Turkovich, that I did. And he calls it make one, check one, move one on, and has some sort of acronym for that thing that sort of looks like moo cow or something. But anyway, there we go. All right, so here are the different forms of coupling. So we talked about FR-FR. If the system is not mutually exclusive, one FR changes at the same time another one does, you need to redefine the FRs. DP-FR, non-diagonal matrices. All right, we looked at that in some detail in the last in part 3 in the last lecture. And then DP-DP and sequential, we just looked at that. So one is a kind of physical integration issue, and the other is a kind of temporal integration issue. All right, let's take a look at measuring design progress and how axiomatic design can help us get the designs done. Let me preface this by saying, as I talk to practicing engineers and I ask, how are you evaluated? The thing that I hear most often is, did I get the design done on time? I said, can anybody tell if it's a good design? They say, nope. But my bosses can't tell if it's a good design or not. They just know if I got it in on time. In fact, there's a guy at the next desk that gets designs in on time, that he knows won't work, but he goes home on time, and I try to make sure they're going to work. Anyway, so here is a graphic that tries to show what happens if you have better knowledge management. There's a paper on that you can read that I've written. Better communications, so improve communications through axiomatic design, and better consensus building. All right, we can build a better consensus through better communications and, as we've talked about, knowing the rules of the game. Now, what happens, and the other thing is, and I've worked in industry, and this happened to me, and everybody I've talked to that's worked in industry says, we never get through any design process without having design changes come in. So here is a little arrow saying, okay, we're going along, we're happily designing this thing, and then somebody decides, well, that wasn't exactly what we wanted, so we need to have a design change. All right, so this sets us back a bit, and here we go. All right, so now we set back a bit. All right, so if we have a coupled design, that means that this one change affected everything, and we can only move along at about the same speed we were before, and you know, by the time we finally get to the completed design, we can see we're way out there someplace, way past the deadline. Why does this take long? Because it requires iterations. I've got a fully coupled matrix, and so as I change one thing, I have to change another. If I have a decoupled design, all right, so then I can tell my design team, all right, you're on this branch, you're on that branch. All right, so this branch, as we've discussed, will have to wait until this branch is completed because this branch is going to do something here that's going to mess this one up, and this branch has to go first. So we know what the order of design is, and we can say, all right, let's concentrate our efforts here on that first DP, and then we'll look at the second, and then the third. So I can organize the design team to move ahead, as long as when that design change hit, I had a triangular matrix. Now, so this requires, as we said, a specific order. All right, so now if I have an uncoupled design, I can put everybody to work on all three branches because they're not influencing each other. I can see exactly what the impact of the design is. It may, in fact, only impact one of the branches. Whoops. And in which case, all right, that's the only one that needs changing. So I have a rather small delay here in the completion time as opposed to these longer delays that we talked about before. So the impact of design changes can be largely mitigated by working on an uncoupled or at least a decoupled design. Cost of change. Let's consider this. So the cost of changing something clearly goes up as we move in this direction from conception to design and prototyping. So by design here, I'm talking about sort of CAD. And so let me make that clear. There's a CAD design, and this is the Eclairo. So I can do the concept design, and the important thing is I can do functional modeling here. And that is using the design matrix. That's what we've just been talking about. This is kind of functional modeling. What DPs are influencing what FRs. So I can very early on, just at the conceptual level, start to eliminate what I can already predict are poor designs. And that's what we like to do as engineers, predict the future. So we can say, you know what, you go ahead with this design, it's not going to work well. Now this can be used qualitatively. One of my students, former students, Mike Shapolsky, was at a company where they were making a device, a plasma torch, that needed a cooling system. So it needs a radiator sort of device like in a car with a water pump and a fan. And somebody said, let's just use one motor to control the water pump and the fan. We can eliminate a part. And at that point, Mike was kind of new. He said, that's not going to work so well, I bet. And the engineers said, no, it's going to be much better. Well, of course, during the course of the design, things got moved around. They had shafts and clutches finally to try to figure stuff out. At least that's what I'm speculating about. And pretty soon they broke down and said, you know what, we need two motors. And that way we can move these two things, put them wherever they work best, where they need to be, and let's reduce that coupling. And it turns out that the two smaller motors were cheaper than one large one anyway. All right, I had mentioned before that Calvin said if you can't measure it, you cannot improve it. So how do we measure design progress? We want to design things quickly. We want to reduce our time to market, and that requires designing good products and good processes to make them. So how do we measure design progress? Well, axiomatic design enables us to measure quality and progress early in the design process. This is like the opening moves of chess. It's not clear how you're going to perhaps win the game unless you're playing against me, and I can never remember how not to move into the 4-move checkmate. And one of the tricks to getting children to bed early, as soon as you win, you can go to bed, but they would fall for that anyway. So what can we measure here? So we've got some things to do. Or some ways of measuring. We can quantify the progress towards the solution using a Claro. We can take a look at is it a good design or isn't it? We have a way to measure the goodness or the quality of the design. So we can reduce uncertainty in predicting the success of a design, and as engineers we like to do that. All right, so we can avoid rushing to particular design solutions, and that is a strong tendency in design groups, because the managers want to see some drawings, and so then they're happy. Oh, I can tell the design's getting done. I see some drawings. Now, whether it's a coupled design or the information content is higher than it needs to be, that's hard to assess, but you can look and say, there's a drawing there. So you need to be careful about this. All right. How far along are you in the decomposition hierarchy? What is the extent and quality of the decomposition? Are you complying with the axioms? How good is your compliance? And then how is the integration going? And make sure, as we showed in the earlier lecture, how is the intent identified? Without the intent, we can't, you can't take, say, a part and say, well, why does it need this? You always have to find somebody and say, why did you put this radius corner in? It's going to be expensive to manufacture. Can we make a bigger radius? They could say, well, you can or you can't or something, but if the intent isn't there, you can't figure it out without getting the guy who did it. And the other thing is, if you're like me, you can do a design and then come back to it in a couple of months and scratch your head and say, why did I do that? Now, obviously, if we work on a flawed concept, that drives up the expense of everything. So we don't want to do that. All right, so how can we avoid some non-value-added activities? Reinventing the same DPs is obviously a bad idea. Using DPs that didn't work before obviously is not a good idea. Redoing decompositions that have already been done. If your company's expertise is in making a certain kind of product, you want to capture that knowledge and be able to reuse that. And that means you go, oh, geez, when I set up this FR, I already decomposed that before. I wonder if I can use the same decomposition again. So if you do these things, you're lacking good knowledge management if you're reinventing the same DPs, right, doing the same decompositions. What if we're designing the wrong thing? Obviously, we want to make sure we're designing the right thing. So there we need good communications. There is designing the wrong thing and designing the thing the wrong way. Those are both problems, and they're not mutually exclusive. You can design the wrong thing the wrong way. Slow adaptation to changes. So we went through that example graphically. So we would like to avoid that. And you get into that because you've got a coupled design or a coupled design process. All right, innovations. We want to innovate. And the contest in the 21st century, at least the beginning of the 21st century, really is to see who can out-innovate somebody else. How do we make a product or a process to make it that is going to be better than what other people have done? And how do designs evolve? Now, I'm talking here clearly about technical innovations and not how do I get venture capital to support this. But if you've done a good design, You can also design your process for getting venture capital, but let's not worry about that. Or how do I make sure there's a need? Okay, that's important too. And we start with the customer needs. So we're really in the mainstream of innovations, innovation technology or innovation methods as we do this. And we need good technical innovations that respond to customer needs, and that's what we've been talking about. Well, how do designs evolve? So we talked about some of this in the first lecture in this series. New customer needs, new FRs, new DPs. New decompositions of the same FRs. New orders of adjustment. You can take an existing design, go in and analyze it with a matrix, and you can say, you know what, you adjust it in this order, and you're going to do better. New physical integrations. Let's get the cup holder out of the middle of the dashboard where the controls for the radio and the tape deck and the defroster are. All right, evolution of design. Evolution requires mutation and selection. Mutation can be favored by getting out of your normal environment. If you do the same thing all the time, you're going to come up with the same ideas. Getting out and interacting with other people who are working on similar problems, maybe in completely different domains, can certainly advance the mutation, just like the evolution of organisms. So how do we, so think about how do you mutate design ideas, and then once you have the mutations, how do you select the best ones? So you can let the marketplace do it, and the companies with poor designs go out of business. We would like to be able to do a little bit more intelligent design and come up with a better solution without just waiting for natural selection to run its course. So, the domains provide a context for creating the ideas, and the axioms are used to sort out the best ideas. Coming up with good ideas is like coming up with good pictures. How do you take good pictures? Take lots of them and look at the best ones. How do you have good ideas? Get lots of ideas, sort them out, figure out what the best one is. All right. What is engineering design? Well, dreaming of things that never were and asking why not or how. So this is conceiving, planning, analyzing, comparing, selecting components and systems. That's what we're talking about with axiomatic design. We want it to be functionally based and objective-oriented. That's what we're talking about with axiomatic design. In fact, what we're trying to do by engineers is create value by thinking. We're perhaps by nature somewhat lazy physically, and if we can think of a better way of doing things that doesn't require so much effort, we would like to do that. All right, so if we're creating value by thinking, then what is thought? Well, as Eric Baum, and we alluded to in an earlier lecture, Eric Baum in his book, What is Thought, says thought is all about semantics. Now, what is semantics about? Capturing and exploiting the compact structure of the world. It's like what Newton did, as we discussed before. So physics is a short list of laws that predict many phenomena. Design axioms are a short list of rules or laws for telling good design from bad designs. And that makes design a science. Sciences are easier to teach, easier to understand, and people that understand axiomatic design can design things better and faster than even experts in the field. Better, faster, and cheaper. All right, what is semantics? Well, semantics is the meanings, relationships, and argument structure that are linked to syntax. All right, so what are we really talking about here? Mathematical equations are part of semantics. And what have we done with axiomatic design? Well, we've developed an appropriate symbolic representation for the design. That's in the decomposition, FR1, FR2, a symbolic representation. We can take these, once we have the design matrix, without knowing what design it is, and then we can restructure that matrix so it is triangular, or maybe target things and say, all right, if we can get rid of these interactions, it can be diagonal even better. So we manipulate the symbols that we've created to characterize or represent the design, and then we can use those to achieve the best design. So how do we look at cost? All right, formulate the FRs appropriately, remove or control coupling, and consider alternative DPs. The best design will be the least cost design that actually works, that is successful. You can come up with perhaps cheaper designs, but they won't be good designs, and they won't succeed in the marketplace. All right, scientists, look at things as they are and ask why. Engineers dream of things that never were and ask, why not? Thank you very much for your attention. Thank you.